Hello, it's Stat 135, Lecture 6. Last time we talked about ways to find the SE of the MOM estimator. One is using a non-parametric bootstrap, and this will give you the SE or the CI. Another way is to do it by hand if you can find a formula for the variance of the estimator. I wanted to go over why bootstrapping works, in particular why resampling from your original sample, at least in the limit, works, as well as sampling from your population. And the reason is, if you look at the CDF for your population, let's call that F. You can compare this with the empirical CDF, which is, for a sample size n, it's the fraction of your sample that's less than or equal to x divided by the total sample size n. So, for example, if x1 is 1, x2 and x3 are both 2, and x4 is 3, then if you have a sample size of 4, the ECDF of 2.5 would be 3/4. And so I've drawn for you what the ECDF looks like, and you can see it closely approximates the CDF, and it's a fact that the ECDF is an unbiased estimator of the CDF, and furthermore, for large samples, the empirical CDF is the variance of the empirical CDF goes to 0. So today we're going to talk about we're going to do another MOM calculation and calculate the SE of the MOM estimator, and then we'll look at a situation where we need the delta method to calculate the SE. And furthermore, and so we didn't have time to start MLE today. We'll do that next time. So here's an example where I have a discrete random variable with a single parameter. I have 10 observations, and you're asked to find the MOM estimate and an approximate SE of your MOM estimate. It was pretty straightforward to calculate the MOM estimate, I think. Furthermore, to calculate the SE, you get to the point where you get a formula for the variance of the estimator in terms of the variance of x, and to estimate the variance of x, because the variance of x is a function of theta and we don't know theta, there are two ways you can do it. One is you could just use the sample variance to estimate the variance, and that's the quick way to do it. Or you could find the population variance using the formula for finding expectation of x squared and expectation of x, and then just plug in the MOM estimator wherever you have a theta, and that'll give you pretty close to the same answer, but is more labor intensive. So here's another example where x is exponential lambda, and you see that the MOM estimator in this case is 1 over the sample mean, and however the variance of the MOM estimator is 1 over x bar, which we don't know how to evaluate, but we can approximate it using the delta method. So the delta method, essentially, it's the variance of a smooth function of the sample mean. So the variance of a smooth function of the sample mean is something that you can approximate, and that approximation is given by the derivative of g evaluated at mu, quantity squared, assuming that's not 0, times sigma squared over n, where sigma is the variance, sigma squared is the variance of x. So to apply that in our situation, we have g of x bar is 1 over x bar. So you just need to calculate the derivative of g prime, plug in mu, and then you can approximate sigma squared as, well, sigma squared is 1 over lambda squared, and you can approximate lambda with 1 over the sample mean. So this gives you the sample error of lambda hat is just 1 over the square root of n sample mean. So here's another example I had you guys practice. If x1 to xn is a random variable with a given density, find the MOM estimator use the delta method to find the SE. So it's just more of the same. Again, easy to calculate the expectation of x, and hence the MOM estimator, because our density is just has one parameter. This is gonna, to find the SE of the MOM estimator, we're going to use the delta method because it just involves x bar. And so we needed to find x prime as a function of mu, and then we just use our formula. It's the first derivative of g applied to mu, quantity squared, sigma squared over n, and then you plug in the estimator for theta in this case, and that gives you your answer. So that was it. It was good practice doing some stuff that you'll need to know for the quiz on Friday, and we will start MLE next time. Have a good day.